I'd like to thank the organizers for giving me an opportunity to give a talk in this seminar. And today I'll be talking about diameter-free estimates for Vinogradov systems. So just to quickly give an idea about the title, what a Vinogradov system is and what do we mean by diameter-free estimates, let's have a quick introduction. So what are Vinogradov systems? Given natural numbers S and K, Vinogradov system of equations is a system of k equations, each having a uniform degree. So in particular, you have s variables on both sides, and you have k equations, and each equation has jth powers, where j runs from 1 to 3 till k. So a quick example would be, let's say we take k to be 2, so we have a linear equation and a quadratic equation, and s to be 3. So in this instance, we obtain the quadratic Vinogradov system. We have a linear and quadratic equation with 3 variables on both sides. And it's a very nice symmetric system of equations. And a classical problem in analytic number theory has been that given a finite set A of integers, we want to know how many solutions does A have to this system of equations. In particular, we are interested in counting the number of 2s tuples x1, x2 till xs and y1, y2 till ys, such that the xi's and y's satisfy the system of equations and they all lie in the setting. I will call the number of solutions to the system jsk of A. Also, because we are in an additive combinatoric seminar, I'll also call this as an additive energy, because we can see it's really counting the number of solutions where all the variables lie in a set A. And so a classical problem has been to find estimates for jsk of A. And recently there's been a lot of progress on that. In fact, 2 very big programs found almost sharp estimates for jsk of A, which in fact are usually of this form. So I don't want to worry too much about the parameters s and k. The point is, you can divide this upper bound into 2 parts. One is a part that purely depends on A, S, and K. And this is usually the sharp part of the upper bound. And you then have an additional factor of x to the power epsilon, where x is the diameter of the setting. In some sense, x is the smallest arithmetic progression in which you can fit your set in. And so, the known upper bound for JSK involve something that is usually sharp times an x to the power epsilon loss. And if your set A is nice, if x is, for example, small in terms of size of A, then you're good, because then this turns into A to the power epsilon. But if your set A is sparse, as in it's very sparsely distributed, as in the diameter is maybe doubly exponential in A, then this x to the power epsilon factor becomes larger than any polynomial power of A, and these bounds perform worse than the trivial estimates. And so we can see that there is sort of a requirement for estimates on JSK of A, which are independent of the diameter x of A. And so in this talk, we'll focus on such estimates. In particular, we'll set k to be 2. So we'll only consider the case when we have a linear equation and a quadratic equation. And to give a quick structure of how this talk is going to be, I'll first give an overview and a list of previous results in the area, talking about both the known approaches to this problem and a diameter-free approach to this problem. Next, I'll present my own result and some applications to related problems, such as discrete restriction and other topics. And once you've done with these, we'll try to prove our main theorem. So we'll first have a preliminary attempt at proving our main theorem, and so we'll get a preliminary bound. And it will be a nice incidence geometric idea to give a nice preliminary bound, but we'll still be missing our main result by quite a bit. And so we'll discuss a 4-step game plan as to how to convert our preliminary bound into our main result. The first step would be something that is called a third energy estimate, which is a known topic in incidence geometric problems. And the second step will be Sumset estimates. These will be the 2 main steps I'll focus on. Step 3 and 4, I'll briefly mention them, but these 2 will form the core of this talk. Lastly, I'll try to give a quick remark about something which I call uniform estimates, and that would be the end of this talk. And so let's get into the overview of what's been happening with this problem. Um, so we want to find upper bounds for JSK of A. Classically, this problem was considered when you fix the set A to be the first n natural numbers. And even in this case, the problem was quite hard. So let's, for the moment, just fix A to be the first n natural numbers denoted by the set AN. And we want to find upper bounds for JSK of AN. And to find upper bounds for something, we should try to figure out what are the known lower bounds, which are usually the more simpler aspect of these kind of problems. So for lower bounds, you can see that there's a very nice lower bound, which is coming from these diagonal solutions. So remember, Vinogradov system had S variables on both sides. You can assume that X1 has n choices, X2 has n choices, Xs has n choices. In total, you have n to the power S choices. And then you can simply set Y1 to be X1, Y2 to be X2, Ys to be Xs. So these are sort of the diagonal solutions where Xi's are a permutation of Yi's. And so you get this diagonal contribution. Moreover, you also have an off-diagonal contribution. And to sort of get an idea of the off-diagonal contribution, we'll first do a nice additive combinatorial trick. So to get a lower bound on energy, we'll first consider the sumset. So I define this curly set A as a set of vectors which lie on the moment curve. So in particular, I take any natural number n, and for that, I take a vector n comma n squared, n cubed till n to the power k. So you can imagine if k was 2, maybe you have a set of real numbers and a parabola, and you're just projecting the real numbers onto the parabola. So any element here looks like a comma a squared or b comma b squared. And once you have this projection onto the parabola, I define a sumset of that set. So this is the L-fold sumset of curly A. If you put L to be 2, for example, you can imagine you're taking any element of the form a comma a square and b comma b square. And when you add them, the first coordinate becomes a plus b, and the second coordinate becomes a square plus b square. And now instead of 2-fold sums, you can imagine this for 3-fold and 4-fold sums. So this is sort of a central object we'll study. Once you have this sumset, and I'll call this Vinogradov sumset, once you have this notion of a sumset, you can imagine that energy and subset can be quite closely related. And in particular, a standard trick in the area, an application of Cauchy-Schwarz inequality, shows that either the energy or the sumset must always be large. And so if you want lower bounds for the energy, it suffices to find upper bounds for this sumset, which is what we'll do in the next slide. So we'll notice that this sumset is a part of the integer lattice, but also this sumset is actually contained in a very nice box. To kind of get an idea why this is true, I'd like to remind you that the first coordinate of any vector lying in the sumset looks like n1 plus n2 dot 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 till ns. Each ni is bounded by capital N. So at best in the first coordinate, you can always get at best s times capital N. So that's s times capital N here. Similarly, in the second coordinate, all your squares are bounded by n squared, and so the total sum will be bounded by Sn squared, and so on till the kth powers. And once you have this nice bound, you can show that the cardinality of this Vinogradov sumset is bounded by the cardinality of this box, which is n to the power k times k plus 1 by 2. And plugging this back into the Cauchy-Schwarz inequality, you get this nice lower bound for the off-diagonal solutions. The reason I introduced the Vinogradov sumset, one of them is to give a very nice interpretation of these off-diagonal solutions, but also this will really be an object of study later in our slides. Combining the diagonal and off-diagonal solutions, I get that the additive energy must always be this large, at least when I'm considering the set A to be the first n natural numbers. And this was conjectured to be sharp. So we now come towards the main conjecture in Vinogradov's mean value theorem. So which says that essentially this lower bound should be sharp up to a loss of n to the power epsilon. So main conjectures stated that for any s and k and for each epsilon greater than 0, one should have JSK of n being less than n to the power epsilon times this lower bound. And in fact, when k is 2, the main conjecture is a classical theorem. You can derive it using some nice divisor estimates. But as soon as you move to a higher degree, even if you go to k equals 3, this was open till quite recently, and it was resolved by Trevor Wooley in 2012 using his efficient congruencing techniques. And the higher degree cases were resolved by Bourgain-Demeter-Guth using decoupling techniques, that is methods from harmonic analysis. So in fact, this very nice looking conjecture was open till quite recently. And so we've got a good idea of how JSK of AN looks like. So if you set AN to be the first 10 natural numbers, we know how the additive energy for this Vinogradov system will look like. So what about the case when A is not the first 10 natural numbers, but any arbitrary finite set of integers? Even in this case, the techniques of Bourgain-Demeter-Guth and Trevor would give nice results. So in particular, their work further implies that even if you have an arbitrary set A, JSK of A will be bounded by what you'd expect to be the lower bound in very nice cases, times an x to the power epsilon, where x is the diameter of the set A. And in fact, their work proves something yet more general. And so I'll introduce what is called a discrete restriction estimate, which goes as follows. So let's say you have any sequence AN of complex numbers, any epsilon, and let's say you're in the regime when S is less than k times k plus 1 by 2. For people who work in the area, this is sort of the regime when the diagonal solutions dominate the off-diagonal solutions. And so it makes writing the discrete restriction estimate a bit easier. So in this particular regime, you have this nice estimate on the 2s moment of an exponential sum. So you have an exponential sum, which has these weights as the complex sequence that we chose. We take the 2s moment and we're able to bound it by the L2 norm of the complex sequence. And to sort of relate these two estimates, one may imagine that x is a natural number, and maybe I'll set an to be 1 for each n lying between 1 and x. And when I do that and I unpack this integral using orthogonality, I see that this actually counts the number of solutions to the Vinogradov system when all the variables lie between 1, 2, 3 till x. Now I can bound this by this L2 norm, but when you put n to be 1 here, you just get n to the power s, x to the power s, which is precisely the diagonal contribution. So we can see that discrete restriction estimates and bounds on additive energy are quite closely related. And so, in fact, if you choose k to be 2, so when you just consider the linear and quadratic system, the x to the power epsilon can actually be explicitly written as e to the power log x by log x. This was a result of Bourgain from 1993. So in some cases, we even have an idea of how this x to the power epsilon looks like. And so we see that when the diameter is small, x to the power epsilon looks very nice. It's actually smaller than any polynomial power of a. But when the diameter is large, say the diameter is doubly exponential, e to the power log x by log x becomes larger than any polynomial power of a. And so these estimates, which had an x to the power epsilon here, perform worse than any trivial estimate. And you always have this nice trivial estimate, which is a basic counting estimate for JSK of A. So really, the cases where the diameter is large, these results perform, they don't perform very efficiently. And so we kind of see why diameter-free estimates could be interesting to study. And one would hope that even in the case when the diameter is large, the extremal cases should precisely look like the ones where the diameter is small. And so one would conjecture that instead of maybe an x to the power epsilon, you would have a size of a to the power epsilon here with the lower bound that you expect. And in fact, when k is 2, this was a conjecture of, this is a conjecture of Bourgain and Demeter. And in fact, they proved a result which makes progress towards this conjecture. So till now, there has only been one previous result in this direction. And for that, they consider the linear and quadratic case, that is when k is 2. And they consider the case when s is 3. And they show that, in fact, you can get an upper bound which is independent of the diameter, but it's not exactly sharp. So just to compare this with the conjecture, if you put k to be 2, k times k plus 1 by 2 becomes 3. So you expect JSK to be bounded by a to the power s plus a to the power 2s minus 3. And when you plug s to be 3, you get a cubed plus a to the power 6 minus 3, which is again a cubed. So in general, you'd expect J32 of A to be bounded by a to the power 3 plus epsilon. So while Bourgain and Demeter could remove the x to the power epsilon, they incurred a cost of a to the power half. And our main result will in fact contain two parts. One improves very slightly upon this result, and the second generalizes result for larger values of S. So we move to the next slide where we talk about our own result. So the first part of our result says that J32 of A can really be bounded by a to the power 3 plus half. So Bourgain and Demeter had an epsilon and an epsilon here, and we could remove the epsilon, though we can see we are still very, very far from the conjectured upper bound. The conjectured upper bound would be a to the power 3 plus epsilon instead of this half. But the novelty of our result is for larger values of S. So for larger values of S, you get a to the power 2s minus 3, which is what the conjectured bound is, plus an exponent which decays exponentially. So as S becomes large, this becomes small very quickly. And you've got a further dampening factor of this 1 minus C. So C is a strictly positive constant. It looks like 0.0005 or something, which makes 1 minus C a constant strictly less than 1. So you've got this exponentially decaying factor and a constant which is strictly less than 1. And so we see that as S becomes large, we get quite close to the conjectured upper bound a to the power 2s minus 3 plus epsilon. Ideally, I mean, this little o1 term ideally should be independent of S, but we could only make this exponentially decaying on S. I think this is a good point to take a quick pause and see if anyone has any questions, and I can take a quick water break. Okay, if there are no questions.
Akshat, sorry to interrupt. Yeah. Can you make that constant explicit?
Which constant? This one, yeah.
Plus 1 for the 3 plus x.
Yeah. Yeah, our methods give a explicit constant. I haven't written that in the paper itself, but the method uses similarity order. So yeah. Anyway, so proceeding forward, we'll now try to prove this result. So let's have a look. Oops, sorry, I should give an application first. I apologize. Earlier I mentioned additive energy and discrete restriction estimates are quite closely related. And so this bound on additive energy that we have can be combined with the bound of Gressman, Guo, Pierce, Roos, and Polam-Young to give a discrete restriction estimate. So as before, we'll take n to be a complex sequence, and we'll consider this 2s moment here. We're taking s to be 3. So we have the 6th moment. And now instead of x to the power epsilon, we have a power of log x, which is better than e to the power log x by log x. But instead of the L2 norm, we have a 12 by 7 norm. So you gain something over the x to the power epsilon, but you lose something in the sense that you have to resort to a weaker norm. And in fact, for a particular class of sequences where the AIs have a very sparse support and the AIs don't oscillate very much, one can see that this estimate gives a better upper bound for this moment over the classical L6 to L2 decoupling discrete restriction estimates. So in particular, the e to the power log x by log x estimate provides a weaker upper bound for a particular class of sparse sequences, which sort of relates to this whole idea that for sparse sets, the x to the power epsilon factor blows up, and so you require diameter-free estimates. And in general, you don't have to focus on the Vinogradov system at all. Our methods, because they're quite different from efficient congruencing and decoupling, and they use more incidence geometry and additive combinatorics, we don't require what is called translation dilation invariance, which is a common theme in efficient congruencing and decoupling. In fact, all we require is some form of convexity. So we can deal with systems which have a linear equation, and we have a symmetric equation of a function psi, which is just convex. So you can take it to be x to the power delta for some delta in this range, or psi x to be log x. And in fact, if you put psi x to be log x, this sort of transforms into a result of a sum product flavor. Which also makes sense because a lot of our techniques are arising from progress which has been done on some product type problems. And in general, you can even replace this linear equation by another polynomial. So so if you have two polynomials, f and g, and they're sort of linearly independent, they have different degrees, you can get non-trivial upper bounds for the additive energy defined by this system. And so these are the applications. And with that, I'll get to our preliminary attempt to prove our main result. So again, let S be a natural number. We come to this curly set A again. So we have a normal set A, which is a set of real numbers, and we project it on the parabola. So any element in this curly set A looks like A comma A squared. And as before, we'll define the L-fold sumset of the set. So the Vinogradov sumset is really all possible L-fold sums where I'm summing vectors in this curly setting. Another useful piece of notation for our case will be the representation function. So given any vector in R2, we use Rs of n to denote the number of ways in which you can write n as an S-fold sum. So I'm asking, basically Rsn counts how many times does a particular sum occur in this set. So as in how many solutions do you have to this equation? With this notation in hand, we can now write JSK of A in a very nice way. So we begin by noting that JS2 of A is really, you'd have a sum over these 2S vectors, and you hit one whenever the S-fold sums equal each other. So this is tautological. This is just representing the Vinogradov system as this nice count. But I can now do something. So I'll write this A1, which lies in A. So I'll write this A1 as simply A. With the rest of the sum here, I'll write A2 plus A3 till AS as V. So now V is A2 plus A3 till AS. So V lies in the S minus 1 fold sumset. And similarly, the right-hand side, AS plus 1 till A2S, I'll write this as U. So now U lies in the S fold sumset. And so I can write this count as hitting a 1 whenever A plus V equals U. But I should also consider all the possible ways in which V can be written as this S minus 1 fold sum, and all the ways in which U can be written as this S fold sum, because that's the case which is truly counting all the solutions. So in which case I simply multiply this factor of 1 with these weights. These weights are precisely how many ways in which you can write V as an S minus 1 fold sum and U as an S fold sum. So this is still a tautology that I can write JS2 as this very nice sum. But the trick comes now. So in fact, what I'm going to do is I'm going to bound this sum as an incidence geometric estimate. So in particular, I can imagine that for any V in the S minus 1 fold sumset, I can consider this curve LV. So this curve is simply the parabola translated by the vector V. And similarly, for each U in the S fold sumset, I can define PU to be U. And the thing to notice is PU lies on this curve whenever U is x comma x squared plus V for some x. So in particular, this sum, which was counting all possible times when A plus V is U, the sum is precisely bounded by the number of incidences between these curves and these set of points, where each incidence is weighted by this factor. So for each curve, I have a weight of Rs minus 1V, and for each point, I have a weight of RSU. So in particular, the sum can be bounded by by the number of weighted incidences. And once I've bounded the sum by the number of weighted incidences, we can use a weighted version of Semerity-Trotter theorem. So when I use this weighted version of Semerity-Trotter theorem, I can show this sum is bounded by some incidence estimate. And because this sum is the same as JS2, I already have nice bound for JS2 in terms of moments of these weights. To get a quick idea of what these weights are, so you take the weights on the points, you take the first moment, you take the second moment. Similarly, you take the weight on the lines, you take the first moment and the second moment, and you take it to the power of 1/3. If all the weights were uniform, if all the weights were 1, for example, you'd get size of, you'd get p square times L square, which is the set of points and set of lines, which is the classical semi-retracted result. So you can see if the weights were all uniform, this would give you the classical semi-retracted result. And you might be wondering, I'm not sure if this has simplified the problem because these sums look a bit weird, but in fact, they have very nice combinatorial meanings. So the first moment of this representation function via a double counting argument is simply a to the power s. And similarly, the second moment is just the additive energy. And so when I plug these back into the previous bound, I get that JS2 of A can be bounded by this nice power of A and JS2 of A and the s-1 fold energy. When I clear out the exponents, I get that I can bound JS2 of A if I have good bounds for JS-1, 2 of A. And so if I know something about this, I can bound the next moment, and I can keep iterating this till I reach just the second, case when S is 2, which is sort of the trivial case. So when I plug this back into this formula, I already get a preliminary bound, which says that JS2 of A is bounded by A to the power 2s minus 3. This is again the conjectured bound that you would expect to hold, plus an exponentially decaying factor. So already using purely incidence geometry, I can get a nice result which sort of approximates the main the conjectured upper bound with a nice decaying exponential factor. So that's kind of nice. Though I'd like to remind you that in the preliminary bound, our exponent was 2 to the power minus s plus 2. But our main result actually had a further smaller exponent. So our main result had an exponent of 2 to the power minus s plus 2, but it was further damped by this 1 minus c factor, which was strictly less than 1. And it's really going beyond this threshold exponent that requires more techniques from additive combinatorics. So I think in some product problems, you usually have a notion of these threshold bounds, which are derivable using purely semi-retracted type results. And it's going beyond these threshold bounds that require various different techniques from additive combinatorics and number theory. And so that will be our focus for the rest of this talk. And so we want to see how we can convert this preliminary bound, this threshold bound, into our main result, which goes beyond the threshold bound. And so we have a 4-step game plan. Step 1 is, instead of considering JS2 of A, we'll consider what is called the third energy. And this is just some ad hoc notation, but I want you to remember that third energy is just the third moment of the representation function. On a couple of slides before, we just saw that JS2 of A is the second moment of the representation function, as in JS2 of A is this formula, except you have a 2 instead of a 3. So instead, we'll bound the third energy, because usually semi-retracted theorem can be seen as a third energy bound. And for this, we'll require the semi-retracted result, but also we'll require an input from the theory of slim exceptional sets. And I'll get to it when I talk about step 1 in more detail. Once we have the third energy estimate, we'll now go to the higher energy machinery, which was originally developed by Schoen and Skredov to bound things such as some sets of convex sequences, or to get to make progress on the sum product results. And we'll use the higher energy machinery for our particular system, which will require multiple third energy estimates, very similar to these. And with this, we'll finally get threshold breaking bounds for the sumset. So after step 2, we'll have bound for the sumset, which are much stronger than the ones that we were getting from our preliminary attempt. And once you have nice bound for the sumset, a classical result in additive combinatorics and many variants of it imply that if you have nice bounds on the sumset, you can get nice bounds on the energy. And so we'll use an inverse result of Skredov to convert these Sumset bounds into bounds for the energy. And now that we have bounds for the energy, we can get good bounds for the third energy, and we'll plug them back into the Sumset and do a couple of iterations to get our final result. And in this talk, I'll mostly focus on step 1 and 2, and I'll not really mention 3 and 4 again. So this is sort of an overview of what happens in the paper. And so I'll start step 1. So I'll just take a quick water break as well. And if there are any questions, I'm happy to answer them. If none, let's start going into what our game plan suggests. So we see that the third energy is the third moment of the representation function. But as before, it also has a nice combinatorial interpretation. So the third energy really counts the number of solutions to this system of equations. And our goal for this section will be to prove that the third energy is bounded by a to the power 3s minus 6 plus some exponentially decaying factor and a log factor. And our experiences with these exponentially decaying factors tells us that in an ideal world, the true conjectured upper bound would be a to the power 3s minus 6, but we have an exponentially decaying factor. That's the best we can prove. And so we'll get with it. So we'll define what are colloquially known as the tau-rich points. So these will be the set of vectors for which the representation function is at least tau and at most 2 tau. So you can imagine that we'll dyadically decompose the third energy into dyadic intervals, and each such interval will be supported on some tau-rich point, on a set which is a tau-rich set. And so if you want upper bounds on the third energy, all we need to do is we need to find upper bounds on this inner sum. I've done a dyadic decomposition. So this capital J is some factor which is bounded by log of the maximum number of representations. There's a polynomial bound for the maximum number of representations, as in they're at most a to the power s. So capital J really looks like log a. So there are log a such dyadic intervals which suggests the log a here. So all we need to do is for each possible j, we just need to bound this inner sum by this factor. And so let's quickly do a particular, let's solve this for a particular type of j's. So all the j's which satisfy 2 to the power j being less than a to the power s minus 3, we can deal with them quite easily. So we have a third moment, but we can take out 2 of these powers and bound them by this factor. So we have a to the power 2s minus 6, but a first moment here. And first moments are easy to deal with. So I have a final bound which looks like a to the power 3s minus 6, which is much better than what I require for the main result. So it's fine if I ignore all these 2 to the power j's because they barely contribute anything. And we can consider all possible values of j where 2 to the power j is bigger than a to the power s minus 3. And for these cases, I can apply the weighted Semerity-Trotter theorem again. And I get this inequality. To sort of give you the philosophy of this inequality, you can imagine you have a set of curves as before, but now your points are not all the set of points, your points are just the tau-rich points. And each point P contributes at least 2 to the power j to the number of incidences. There are a total of P tau set of points. So this is really a lower bound for the number of incidences between the set P tau and your usual set of curves. And we can upper bound the number of incidences by this Semerity-Trotter type estimate. So you have a main term and an error term. In fact, I'm actually hiding a second error term which we could throw away because of this particular condition. And even before in our preliminary attempt, we had 2 error terms, but they were not really, they could not dominate the main term. So I carefully ignored them. But this is the inequality you get when you apply Semerity-Trotter theorem. And so our proof divides into 2 cases. What happens when this term dominates and what happens when this term dominates? So simplifying exponents, the inequality implies that the number of Tauridge points is either bounded by this main term or this error term. And usually, as is in this in these type of cases, if the main term is dominating, you're usually in good hands. So in particular, when 2 to the power j is small, which is precisely the case when this term dominates, I'm actually quite good. So just using this inequality again, I see that p tau times tau cubed, I'll just call 2 to the power j tau because it's easier. So p tau times tau cubed is bounded by this main term, which using our preliminary estimate gives us the correct upper bound. So this is really a to the power 3s minus 6 plus some exponentially decaying factor. And since there are at most log a such 2 to the power j's, I'm happy in the case when 2 to the power j is small. And just to reemphasize, I'm happy when the main term is the dominating term. So what about the other case? What happens when the error term dominates? And actually that's the trickier part. So when the error term dominates, that is when 2 to the power j is sort of large, I'll try to use this inequality again and see what I can get. So when I try to use this inequality to get a third moment estimate, I have an upper bound which looks like this. Remember 2 to the power j can be as large as the maximum of the representation function. So this is a reasonable step. But now I'm stuck because I have no non-trivial bounds for the representation function. And so what I do here is I just put the trivial bound for the representation function, which is this. But now I'm in a problem because this bound is a to the power 3s minus 5, which is much bigger than 3s minus 6 plus some exponentially decaying factor. So just using purely incidence geometry cannot give you good third energy estimates. And this is sort of where the number theory input comes in. So this is a lemma called averaging over exceptional sets. This was originally used in a paper of Trevor on slim exceptional sets for sums of 4 squares and some related work. So the idea is instead of trying to find pointwise bounds for this, for p tau times tau, what you do is you average over all such taus. So whenever you have all these large representations, you can actually get what you can think of as an L2 bound. I say it as an L2 bound because there's a tau here, there's a tau cubed here. So this is really a bound on p tau times tau square. So instead of this L1 bound, I will use this L2 bound. And I would not prove this lemma here, but it's quite a nice and simple proof. But it precisely gives us what we require. So assuming this lemma to be true, assuming that for all the large representations, you actually have a nice bound, this lemma actually delivers us the required bound. And you can see this because p tau times tau cubed is bounded by this. This factor a times tau, I can now use trivial bound for tau again, and this gives me a to the power s minus 1. I have a preliminary bound for this, which is 2s minus 5 plus this decaying factor. And multiplying these together, I get precisely what I required. And again, there are at most log a such taus, so I get the main result. And so using a mix of number theoretic and incidence geometric ideas, I can get a good bound on the third energy. So that's step 1 done. Step 2 is now to go from third energy to good sumset bounds. So just to quickly remind you what we have done till now, we have shown that the third energy can be bounded in terms of some nice power of A and the second energy, and we have preliminary bound for the second energy, and we plug them in to get this main third energy bound. I'm using this squiggly notation from now on. All this squiggly notation does is it hides constant powers of log A, because trying to keep a track of how many powers of log I have is a bit messy. So I'm just hiding powers of log A under this notation. And so now we want to consider bounds on sumsets. So just to keep it simple, I'll consider the case when S is 4. And so instead of considering 4A, I'll look at 2A minus 2A. The reason why 2A minus 2A is nice is just some technical reasons. But in particular, I'm looking at any sumset which looks like A1 plus A2 minus A3 minus A4, and then the symmetric version for the squares, where all the AIs are varying in my setting. So I'm looking for lower bounds for the cardinality of the set. And remember, we had this trick at the starting that the energy and the sumset both can't be small simultaneously, and that was coming from a Cauchy-Schwarz inequality. So instead of Cauchy-Schwarz, you can use Holder's inequality and get and show that either the sumset or the third energy must always be large. They can't be simultaneously small. I'm actually sort of lying here. It's not really K42 which should be here. It's a variant of K42, but for our methods, for our paper, and really for the purposes of this talk, you can really look at K42 and everything works similarly. So ignoring that comment, the third energy and the sumset, they can't be small simultaneously. And because we have upper bounds on the third energy, we can plug them here to get lower bounds for the sumset. So when we plug these third energy bounds, we show that the sumset 2a minus 2a is at least a to the power 3 minus 1 by 4, which is a nice bound. But we are actually being quite wasteful. We worked this out with a lot of hard work, and then we're just applying a Cauchy-Schwarz to get this sumset bound. And so this is the main motivation of higher energy methods. Higher energy methods say that under some technical assumptions, ideally, you can always get bounds which are stronger than just Holderizing the third energy for some sets. And so I'll write a lemma here. I call this the higher energy lemma. This is a culmination of multiple third energy type estimates and multiple Cauchy-Schwarzing and pigeonholing type arguments, which are usually present in these higher energy methods. But the conclusive lemma appears like this. So again, this lemma says that the sumset and higher energy can't be small simultaneously, but now I have more weight towards the sumset. So earlier I just had 2a minus 2a squared, but now I have 2 plus 3 by 4. So somehow this should already tell you that I have better estimates for the sumset from this higher energy lemma. And just for a moment, if you assume that Cauchy-Schwarz was sharp, if you assume that the third energy is in fact, as in if the equality held in the Cauchy-Schwarz inequality, then I could plug this into the higher energy lemma to get 2a minus 2a is as big as a cubed, which is in fact as big as we could get, because you could imagine a can be 1, 2, 3 till n. So trivial upper bound for 2a minus 2a is just n cubed. So we can already see that the higher energy arguments are a much more strengthened version of the Cauchy-Schwarz lemma. And in particular, if we, as you can see, the higher energy lemma strengthens the Cauchy-Schwarz bound. And if we just plug in the third energy bounds that we got in the previous section, we get this inequality. Here I've just plugged in the bounds for K42 of A, as we did before. To simplify the exponents, I get 2a minus 2a is greater than a to the power 3 minus 2 by 11, which is a to the power 3 minus 1 by 4 times a positive power of a. So just to recall, this was the bound that we were getting using third energy bounds and Cauchy-Schwarz. So we can clearly do much better than Cauchy-Schwarz. You can have a proper power saving using higher energy methods. And because of a lack of time, I couldn't say much about step 2, but essentially the idea is we can use inverse results. Now that we have threshold breaking bounds for the sumset, we can use inverse results to get threshold breaking bounds for the second energy. And these use more higher energy methods along with some simple ideas from additive combinatorics. And now you can iterate this, because remember our third energy was bounded in terms of the second energy. So I can plug them back in for the third energy to get new estimates for the third energy. So this was the bound that we just had for the third energy. And this is still true when s is greater than or equal to 3. But as soon as s is greater than 5, we can actually get much better bounds. So we can replace this exponential factor by a smaller exponential factor. And now that we have better bounds for the third energy, we can plug them back into the higher energy lemma to get much better bounds. And you can iterate once again, but you can only iterate once again because this S becomes large and you don't have this higher energy lemma again. And so to sort of quickly summarize, after a couple of iterations, you get our main result. And to sort of give a quick review, a quick summary of the paper again, I'm going to try to compress it all in the form of sumset estimates. So we return to Sumset estimates. And for any S, we write Z of S to be the best exponent that we can get for this inequality. Just to remind you, if I put A to be the first 10 integers, this is always bounded by n cubed. So when S is greater than or equal to 2, we really want ZS to be little of 1. We want it to be as small as we can get it to be. And we really expect ZS to be little of 1 anyway. So this is a big table, and I'll go through it systematically, but this sort of tells you all the methods that we use in our paper. So at first, we used purely incidence geometric bounds. This was the preliminary attempt that we did. And using the preliminary attempt, the value of ZS that we had was 4 to the power minus S plus 1 for all values of S greater than or equal to 1. Then we started working hard. We used higher energy, but then we used inverse results to get bound for the energy. And now Cauchy-Schwarzing this energy again, we can get another bound for the Sumset. So using this as a black box and applying Cauchy-Schwarz inequality, we can reduce ZS, but by a very small constant, like by a constant which is just smaller than 1. Instead of using these, if we apply our higher energy method directly, we got 8 by 11. This should be reminiscent of 3 minus 2 by 11. So we can get 8 by 11 times the exponential factor. So just using Cauchy-Schwarz in our main result, you get a constant which is strictly less than 1. But using higher energy, you can get a much better constant. You get an explicit 8 by 11. And in fact, if instead of applying higher energy for 2a minus 2a, you apply it for 3a minus 3a, you get an even better constant. But this is only true for S greater than or equal to 3. So for 2a minus 2a, this is still the best bound. But for larger values of S, you can apply higher energy directly and get better exponents as you go on. And then you can take these, put them back into third energy, feed them back. And so our main result can do slightly better than the higher energy results themselves. So you can sort of see this is the natural progression of our paper. We keep getting multiple bounds, and we try to do better at each step using an additional technique, which culminates in the final bound, which looks like this. And in 1 minute, I'll quickly like to summarize what all we have done. We have looked at bounds for the second energy, the third energy, the Sumset. In some sense, these can all be seen as various moments of the representation function. So any bound on the second energy is a bound on the second moment of the representation function. Any upper bound for the third energy is a bound for the third moment of the representation function. Similarly, in the previous slide, which I just very quickly skipped, we could get bounds for the representation function in general. So if you define Rs of A to be the maximum value that the representation function can take, we can even get upper bounds for the representation function, which can be seen as an L infinity norm on Rs. And similarly, the Sumset can be seen as the size of the support of the representation function. So in general, this study has basically been considering various norms and moments of the representation function. And with that, I'd like to say thank you